Hello! Welcome to the introductory video on problem solving and critical thinking. You might be thinking about the kinds of math courses you've taken in the past and the kinds of problems you were required to solve. You might be feeling a little bit uneasy about those sorts of things, but don't be scared, because the kinds of problem solving and critical thinking that we'll do in this course are the kinds of things you do every day. So in order to understand critical thinking and problem solving, reasoning is the answer. Reasoning is something that we all do every day. Reasoning happens when our senses gather information regarding our present situation or surroundings. The information that is gathered is processed in our brains. Through the act of reasoning, our brains interpret the information it has collected based on our prior experiences and knowledge. If our brain doesn't have any prior experience or knowledge of the situation, we cannot process it until we learn more. Reasoning is commonly associated with problem solving, critical thinking, and decision making. So here's a simple example of reasoning. So if you woke up this morning and your senses told you that it was going to rain today, you then will use reasoning to make a decision or come to a conclusion. You might decide that it's important to take an umbrella. Others might decide it's important to wear a cap. And still others may think about having to run from the bus stop to the office to keep from getting wet. So even though we each observe the same thing, we may come to a different conclusion based on our life experiences and our knowledge of the situation. Now, just how is math related to reasoning? Well, math actually equals reasoning. We all already have reasoning ability, but taking what's there and improving it will just make us a better general problem solver. Problem solving ranges from the simplest thing, such as what you're going to have for dinner, to even more complicated things such as how to end world hunger or build a manned rocket that can travel to Mars. So each of these things involves some kind of problem solving or reasoning to come to a conclusion. Some kinds of problems are easier to solve than others. But learning mathematics and the systematic methods for solving the various types of problems we'll encounter will translate into the ability to be a better overall decision maker. And being a good decision maker translates to every area of your life. Among some areas are things such as the courses that you're going to take to graduate from college, things at your place of employment, and of course there are always consumer and personal decisions to be made. So let's talk about some of these specific areas in life where math is really useful. Because we really are all problem solvers, and we do use processes that we learn in math to actually solve problems that we encounter daily. For example, most other courses that you're going to take in college will require some kind of math or problem solving technique that is specific to problems in that field. There are graphs and tables to read and interpret in courses such as history or sociology. There are ratios to calculate in art or nursing or chemistry. And then in some courses there are functions to evaluate such as economics, accounting, or physics. And these are just a minor handful of the thousands of examples of how math and problem solving is incorporated into every course in your college career. Even something as simple as bowling will require that you learn the process for keeping score, and that process is a mathematical process. And in employment, most jobs involve some form of math, whether it's as simple as calculating the weekly hours that have been worked, or calibrating a machine to the nearest millimeter, or maybe determining the amount of fuel that's needed for an airplane to travel from New York City to Chicago. So while on the job, the math may be something simple, or the math may be something that's very complicated and part of a life or death situation. And of course, we all have consumer and personal decisions to make throughout our lifetime. And often, these kinds of decisions go hand in hand. Questions like, can we afford to buy that car? Or, is it now time for us to start a family? Or maybe add to our family by having another child? Or it could be something as simple as, I saw these really cool jeans that were on sale. And can I purchase them? Does it fit into my budget? So whether you're using the math from this course in another course you take, on the job, or in a consumer or personal decision, you'll be solving problems of this type throughout your lifetime, because we are all problem solvers. So to become more comfortable with the process of solving problems, it's important that you know and understand this process called reasoning. And once you can understand some of the reasoning processes that go into making decisions, you'll be a better problem solver. Not only will the reasoning and mathematics in this course help you with other courses you must take, it will also help you with your employment and the kinds of personal and consumer decisions that you will make throughout your life. Now, it's very important that you understand the vocabulary or definitions that are associated with reasoning. The first thing to know is inductive reasoning. Inductive reasoning occurs when a specific example is observed, or perhaps a number of examples are observed. And then, based on those specific examples that have been observed, a general conclusion is made. So you observe something specific, you think about what you've observed, and you come to a general conclusion. This is the process of inductive reasoning, starting with a specific, coming to a conclusion that is general. This process is also known as induction. When you reach a general conclusion based on a specific example, you have participated in inductive reasoning or induction. Here are some other words you should know. Conjecture or hypothesis. Now, these words are interchangeable and mean the same thing. Any conclusion reached through inductive reasoning is called a conjecture or a hypothesis. So again, the two words are interchangeable. You reach a general conclusion based on specific examples. That conclusion is a conjecture, or that conclusion is a hypothesis. Now, it's important to note that general conclusions based on specific examples, that is the process of doing inductive reasoning or inductive arguments, are really also just educated guesses. And while adequate observations may provide strong evidence and support for your general conclusion, any general conclusion that's reached through the process of induction can never be proven as 100% true. You can, however, prove that your conjecture or hypothesis, that conclusion that you've reached based on inductive reasoning, is false. And the only thing you have to do to prove it's false is to provide a counter example. So let's take a moment to look at an example of inductive reasoning. Remember that with inductive reasoning, we'll start with something specific. We think about what we've observed, and then we come to some general conclusion called a conjecture or hypothesis. Let's talk about trial by jury. In a trial by jury, there are a lot of specific observations. If you're on a jury, you will be presented with specific details, observations by both a prosecution team and a defense team. Then you have to take those specific details into the jury room and think and reason with your juror peers to come to the conclusion of guilty or not guilty. So the specific information are the facts that are in evidence, whether those facts are given by the prosecution or if the facts are given by the defense. There's still thinking and reasoning that goes on, and then you make the conjecture of guilty or not guilty. And it's important to remember that the ability to convict based on specific observations in a trial by jury involves inductive reasoning. So the juror's belief in the guilt of the defendant has to be beyond reasonable doubt. That is, you've done inductive reasoning to remove most of the doubt, but it is not beyond all doubt. And that is because any inductive reasoning that has taken place can never be proven 100% true, but it can be proven false by a counter example. So let's look at another example of induction or inductive reasoning. The last 10 times you've been walking at the park, you have noticed many people are walking beagles. So you think about that for a few minutes, and you come to the conclusion that the beagle is the most popular dog in America. Now, while these observations may provide a very strong amount of evidence and support for this general conclusion that you've made, this cannot be proven by these methods. Who knows? Maybe the Beagle Rescue Club meets at the park the same night that you walk there. And also, the American Kennel Club would argue that the Labrador Retriever is the most popular dog in America because that dog is registered with the American Kennel Club more than any other dog and has been for the past 5 years. And then the argument can be made for the Labrador Retrievers that aren't registered, or dogs that aren't fully Labrador Retrievers, or just your common, ordinary, everyday mixed breed or mutt that many people have. So just by walking in the park, you've come to a conclusion through inductive reasoning, and it's a general conclusion that might be proven false by many different counterexamples. So it's also important for you to understand the word counterexample. Any single specific case that shows a conjecture or hypothesis to be false is called a counterexample. So even if you observe something a large number of times, a single counterexample can prove a conjecture or hypothesis to be false. Now later in this course, and in a course on statistics, if you take that course, you will learn that we can predict our hypothesis to be true within a certain range. So while it might not be possible for us to prove with 100% certainty that our hypothesis is true, we might be able to show that there's a 99.99% chance that it's true. So let's look at a counterexample, keeping in mind that a single counterexample can prove a conjecture or hypothesis to be false. So in this case we have a math example. We have some division facts. We have our dividends. We have our divisors. And we have our quotients. After observing the numbers for a few minutes, there's a general conclusion reached. And that is that when one whole number is divided by another whole number, the quotient, which is the answer or result of division, is always smaller than both the divisor and the dividend. So if you look at the first column of dividends and then the divisors, and you look at the quotients in our specific examples, you will see in each case the quotient is smaller than both the dividend and the divisor in the problem. So our general conclusion seems to make sense based on these three limited observations. However, here is a counterexample. Since 8 is not smaller than both 16 and 2, our general statement is proven to be false. So it's important that when you use reasoning by induction or inductive reasoning, to understand it can't be proven true, and that a counterexample may actually prove that your inductive reasoning is false. Maybe enough examples have not been observed. Or maybe the generalizations are just so broad that they can't be proven by this method. And in everyday life, induction is used to stereotype certain situations. For example, you might hear a very broad statement such as, all pit bulls are mean, aggressive dogs that should be put to death. But there are plenty of people who can provide a counterexample to that statement, because they have very nice, loving pit bulls that would not harm any person, child, or small animal. So even one counterexample can prove this very broad generalization or stereotype to be false. Here's another example. Any young person without a job is looking for trouble. And in this case, to prove this false, all you have to do is find a young person who doesn't have a job, who's not looking for trouble. For example, you may not be employed. You may be looking for a job. Or you may be a full-time student. So just because you're without a job doesn't mean you're necessarily looking for trouble. So perhaps this generalization was made because a number of young people without jobs were observed to be getting into trouble. But all you have to do to prove this false is to provide a single counterexample. So this observation of specific young people getting into trouble because they don't have jobs cannot be used as an argument to say that all young people without jobs are necessarily looking for trouble. So using induction to make a broad sweeping generalization can be unfair, and can never be proven as 100% true. So now we're going to use inductive reasoning to recognize patterns or trends in a list of numbers. Now the reason this is inductive reasoning is that we're going to start with a few specific examples. So now we're going to use inductive reasoning to recognize a pattern or a trend in a list of numbers. Now remember, this is called inductive reasoning because we're going to start with some specific examples. We're going to think about those specific examples, and we're going to come to a general conclusion. So this is a process of inductive reasoning. So here's our list of numbers: 2, 7, 12, 17, 22, blank. So we want to find the number that belongs in the blank. Your first observation is probably that these numbers are getting larger because we're going from 2 up to 7, from 7 up to 12, from 12 to 17, and then 17 to 22. And often when numbers increase, that means that a particular number may be added to each number to get the next number in the list. So if we observe what happens when we go from 2 to 7, we will notice that we have to add 5 to get from 2 to 7. And then to get from 7 to 12, once again, we'll be adding 5. And if you continue to observe these specific examples, you will notice that each time, in order to get from one number to the next number, you're going to add 5 to the previous number. That means for our blank, all we have to do is take the 22, add 5 to it, and come up with 27. So we observed 5 specific examples, starting with 2, and then adding 5 for 7, and 5 for 12, another 5 for 17, another 5 for 22. We came to a general conclusion that we needed to add 5. So let's look at another example of using inductive reasoning for recognizing a pattern or trend in a list of numbers. So in this list of numbers, we have 1, followed by 10, followed by 100, then 1,000, then 10,000, and now we have to find that 6th number that would appear in this list. This is inductive reasoning because we're going from these specific examples and we're going to come up with a general conclusion of what is done in order to move from one number to the next so we can fill in the blank for that 6th number. Just like before, these numbers are increasing. However, before we saw that they were increasing by the same amount, so we could come up with that general conclusion that you add 5 every time. In this case, however, adding is not going to be our general conclusion, because if you go from the first number 1 to the second number 10, you would add 9. But then from 10 to 100, you have to add 90. So you can't say you add the same number every time. Like we said, we added 5 every time in the last example. However, we do notice that the numbers are getting larger, and we also notice that each time we move from one number to the next, there's an additional 0. So in the number 1, there are no zeros, but in the number 10, there's a 0. And in the number 100, there are 2 zeros, then 3 zeros in 1,000, and 4 zeros in 10,000, which helps us come to the conclusion that we need 5 zeros. And that is, in fact, the next number in the pattern, a 1 followed by 5 zeros. That is the value 100,000. Now, our general conclusion, mathematically, is that each time we moved from one number to the next number, we multiplied by 10, because that's what happens when you multiply by 10 if a number ends in 0. Because that's what happens when you multiply a number that ends in 0 by 10. A 0 gets added on to the end of the number. So if we multiply 1 by 10, we get 10. If we multiply 10 times 10, we get 100. If we multiply 100 by 10, instead of 2 zeros and 100, we have 3 zeros and 1,000. Same thing for 100 to 10,000. You multiply that by 10, you get 10,000. And then if you multiply 10,000 by 10, you'll get 100,000 or 5 zeros. So our general rule here is that you multiply by 10. Now, when you're using induction, you need to proceed with caution, because you're going to start with specific examples and you're going to come to a general conclusion. So you need to make sure you have sufficient evidence to come to that general conclusion. So let's take a look at a different kind of pattern of numbers, complete the next line, and see if we can come up with a suitable general conclusion. The first number in the pattern is the number 1. So we can't really predict what the next number might be simply based on a single value 1. I now have more evidence, and I see that I started with a 1, and now I have another row, and it has 2 1s in it. So I can make a general conclusion about this and say, well, if I've got 1 1 and then 2 1s, then perhaps this pattern is to have a series of 1s where there was always one more 1 in the next row. So here I've drawn sort of this triangular pattern of 1s where there's a single 1, then 2 1s. The third row has 3. The fourth row has 4. The fifth row has 5. And based on what I've seen so far, this seems like a logical conclusion to reach. Let's see what the next observations will tell us. Okay, now that we have our third row, we see that the third row is 1, followed by a 2, followed by a 1. So the conclusion that we reached, that this is just a set of 1s where there is one additional 1 in each subsequent row, is no longer valid because we now have a counterexample. And that is that the value 2 changes everything and tells us that this can't be a triangle that just has 1s. Now, we can continue to observe that there are 1s in every row when you start and in every row at the end, and so that part is still true. So let's take a look at the next row. This might be exactly what you would predict. In row 4, there are 4 numbers. Starts with a 1, ends with a 1, and then the numbers in between are 3 and 3. So we're in row 4. We have 4 numbers, a 1 followed by a 3, followed by a 3, followed by a 1. So now we can see more of the pattern. We notice that our trend of 1s starting the row and ending the 1 has continued. But now we can see also that whereas we started with 1s, then we had a 2, then we had a 3, that maybe our pattern is that within each row between the 1s, you have a number that's 1 larger than those numbers that were in the previous row. So whereas we had 2s and 3s, we would now have 4s to make our 5th row. And since we're in the 5th row, we started with 1 entry, then 2 entries, then 3 entries, then 4 entries. Now in the 5th row, we need 5 entries, starting with a 1, ending with a 1, meaning that we would need 3 4s. So, based on what we see, looks like a pretty good argument for our general rule. One more row. Now we have another counterexample, which proves our previous conjecture to be false. Because now, instead of having all 4s in this row, this 5th row, we actually have a 1 followed by a 4 followed by a 6 followed by a 4 followed by a 1. So this value of 4 that we thought would be in this row and having all 4s in between those 1s is really a 6. So now we've got to look closer at what our pattern is. Our 1s as the first number continue the trend, and as the last number continue the trend. The trend continues where you start with 1 number and then 2 numbers and then 3 numbers followed by 4 followed by 5. So this tells us we probably have 6 numbers in the next row. We'll start with a 1 and we'll end with a 1 because that conclusion or conjecture has not been proven false by counterexample. And so now we know, since we're in the 6th row, starting with a 1 and ending with a 1, we need 4 additional numbers. So we need to observe what's going on with these numbers. And until we got to that 6, it was a little bit hard to see. But I think if you look at the 2 numbers that are above the number to its left and right, you will see that when you add these numbers, you'll get the number below. So 1 plus 3 gives the 4 below, 3 plus 3 gives the 6 below, 3 plus 1 gives the 4 below, and we can even go back to the previous row to see that that is also true, that 2 and 1 is 3, and 1 and 2 is 3, that if you add those together. So now we start to see what our real pattern is, that each row begins with a 1 and each row ends with a 1, but to find the next number, we take the sum of the 2 numbers above. So 1 and 4 would be 5, 4 and 6 would be 10, 6 and 4 would be 10, and 4 and 1 would be 5. So that in our 6th row, we do have 6 numbers, a 1 followed by a 5, followed by a 10, followed by a 10, followed by a 5, followed by a 1. And each of those numbers, with the exception of the one that starts the row and the one that ends the row, is the sum of the 2 numbers directly to its left and right above it. Now that we have our general conclusion, you can take that general conclusion and you can complete another row of this pattern. Since this is the 7th row, you'll need to complete 7 numbers. We know it starts with a 1 and it ends with a 1, so there are 5 missing numbers for this row. I want you to take just a couple of minutes and see if you can fill in those numbers that would be in that 7th row of this arrangement or pattern of numbers. So if you haven't finished, you can pause the video and finish your row. And now we'll talk about what numbers should be in the 7th row. If you add the 2 numbers above it, you would get a 6, you would get a 15, you would get a 20, you would get a 15, you would get a 6. Now, if you got that right, you're using the process of inductive reasoning to take some specific examples and come to a general conclusion about how something works. If you missed it, go back and look at the numbers, kind of clean the triangle up and rewrite it and look at the numbers and think about how it is that this pattern emerged. You'll find other patterns in this triangle. So this particular triangle of numbers is actually a very famous triangle that's called Pascal's triangle. And it's got even more patterns and trending in there that you can find if you explore it further. So now that we've become familiar with the process of inductive reasoning, that is moving from the specific to the general, we're going to look at the other type of reasoning. This type of reasoning is called deductive reasoning. Deductive reasoning occurs when general statements are used to prove a specific conclusion. So we're going to begin with the general this time. We'll do our thinking and reasoning, which this time is deductive reasoning. And we'll come to a specific conclusion. And that specific conclusion will actually be proven to be true. Because with deductive reasoning, you actually can have 100% certainty that your conclusion is true. This is the process of deduction. So when you prove a specific conclusion from one or more general statements, you've participated in deductive reasoning or deduction. In our example here, we're asked to find the measure of angle C. And we're given the diagram of a triangle where angle A is labeled as 60 degrees, angle B as 90 degrees, and then angle C is missing. So we've got to find the measure of angle C. So we're going to start with a general statement about triangles, and we're going to use our deductive reasoning to come up with a specific value of that angle C. So here's our general statement. The sum of the angles of any triangle is 180 degrees. So what this says to us is that if we add up angle A plus angle B plus angle C, it must equal a total of 180 degrees. So I'll switch this over to the symbolic form. So A plus B plus C, or the measures of A plus B plus C, have to equal 180 degrees as given to us by our general statement, which we assume to be true. And then we know that A is 60, and we know that B is 90, and we know that the total is 180, so we can now determine the value of C because we have enough information to do that. So since the first two angles of 60 and 90 degrees add up to 150, we now can conclude that angle C has to have a measure of 30 degrees. And the reason we know that is these three angles must, by this general statement, add up to 180. If we take the 60 and the 90, we've got 150. We must have 30 degrees more to get our total of 180 degrees. So we can find this answer by the process of using an equation such as the one you see here, or by also just using arithmetic facts, knowing that you have to have 180 degrees total. You've used up 150. That leaves us with 30 degrees as our specific conclusion. So we started with a general, we ended up with a specific, and that is the process of deduction. So sometimes we'll be asked to determine which type of reasoning is being used. And so in order to do that, you must decide, are you starting with specific or general, and are you ending up with specific or general? So you have to observe the kinds of information you're given, decide if it's specific or general, observe the kinds of conclusions that are shown, are they specific or general, and then you can indicate the type of reasoning that was being used. So here's our first observation. Roger just heard on the news that a child had been abducted by a man in a green van. And from that information, Roger makes the conclusion that people who drive green vans are bad people. So Roger started with a very specific piece of information. He took that specific information and he came to a conclusion that's very general. Because Roger is now saying that people, and that's people in general, who drive green vans are bad people. This is an example, from the specific to the general, of inductive reasoning. And of course this could never be proven true, and in fact it probably could be proven false by finding someone who drives a green van who's a very good person. So here's another example where we have to determine what type of reasoning is being used. Our first observation is this statement. All men in the United States must register with the Selective Service upon reaching the age of 18. Miguel has registered with the Selective Service. Here are our observations. A statement that says that all men must register with the Selective Service when they reach the age of 18, and that Miguel has registered with the Selective Service. And finally, here's our conclusion. Miguel is at least 18 years old. So we started with something that was pretty general. And that is that rule that upon reaching the age of 18, all men must register with the Selective Service. And we've come to a specific conclusion that Miguel is at least 18 years old. So when we start with a general statement and come to a specific conclusion, we have participated in deductive reasoning. So those are the distinctions. Specific to general, inductive reasoning. General to specific, deductive reasoning. And our final definition for this video is the word theorem. When a conclusion is proven to be true through deductive reasoning, the conclusion is then called a theorem. And proving conclusions through deductive reasoning is a topic that we will cover later in the course. So at this point, you don't need to worry so much about proving conclusions as you do understanding the difference between an inductive reasoning situation and a deductive reasoning situation. And you'll be using both inductive and deductive reasoning throughout this course in order to think critically and solve problems.